Hi. So today I'm going to talk about the Algorithm Design Manual by Steven Sekina. And as much as this book tries to help you understand and resolve all the problems that exist, it doesn't do it explicitly by giving you all the possible solutions, but rather it tries to shift your perspective on how to resolve a problem or how to design an algorithm. And that automatically shifts your methodology to resolving a problem at hand. And this goes the same for the main idea, which is pretty much it, the same thing. So basically, the resolution of an algorithm is no longer about designing it or building it from scratch, but rather sensing the pattern of that problem and using the tools that already exist based on that pattern to choose them and compose them in the right way for your solution. So you can get an initial or a skeleton of your solution that you can proceed with. So that's pretty much it for the main idea of the book that the author tries to prove. And through our discussion, we're gonna go just on the main or necessary pillars so we can have a concrete vision of this idea. And since we're going to talk about what we're going to discuss in this presentation, we're going to talk about correctness and performance for an algorithm, what that mean, and data structures. Then we're going to talk about graphs and their use cases. And then we're going to discuss NP problems and the NP concept itself. And from there, we're going to understand how to resolve an NP problem and basically through combinatorial research or dynamic programming, for example. Then we're going to talk about reduction and its link with NP concept. And at the end, we're just going to give an approach on how to design algorithms based on what we discussed. So people think that performance is the main thing for a perfect algorithm or it's the crucial part. But the necessary and the most important piece that you need in your algorithm to function and to be a well-positioned algorithm, which is correctness. Because at the end, an effective algorithm is the one that's not working normally just on the normal cases, but on the edge cases and the abnormal cases that exist. And you cannot make sure that works only by thinking like for common sense or reasonable way of thinking through the normal solution that you want to resolve for the problem. But you need to prove that the algorithm is going to behave correctly through all the cases. And there is different ways you can do it. There is no, let's say, methodology or something that you can follow, but there is some logical, uh, let's say, routes that you can take. Uh, an example is you can use counter examples to disprove your solution, and this is really important to test, for example, for heuristics or what I mean by heuristics is when you try to find a solution that's just through a heuristic way instead of planning it logically. Also, if you have a solution that is incremental or recursive, you can use mathematical induction to prove its correctness. And yeah, that's a way that you can prove correctness, but that's not the only ways. You just need to find how to prove that your algorithm is going to work, how you want it to behave in all the cases that exist. When you finish with correctness, then you can go to performance because at the end of the day, we have a computation challenge always in our industrial or real life implementations. And to measure the performance, we need to have a framework that we should follow or a measure that we can quantify the performance of our algorithms. And this is where the big O notation come, which is basically a way that we can switch the process for our algorithm to a function, and that function will represent it through the input that we put to our function. So when you change the endpoint, the function will change, and which will give you an idea about the performance, either a space performance or a time performance. But most of the time, we calculate the time performance here. And when we have that function, we don't precisely calculate the time exactly, but we can round up that function to the high order of that polynomial or whatever function that we have there, and use that as a rule of thumb to know how our algorithm behaves. For example, if the complexity is quadratic, which is can be really drastically not efficient when with inputs at scale. However, if the complexity is logarithmic, then we can know that our algorithm can behave really efficiently and performantly in high scale inputs. Another way to increase the performance is, or one of the big parts that you can sorry, increase performance, which is data structures, the choice of the data structure that you're using in your algorithm. And basically, you should not see data structures that just mean of storage, but you should see them as tools to make your problem or your algorithm problem run efficiently. And the choice of each data structure can change through the behavior of the algorithm that you have. For example, you cannot use the same data structure that's performing really well in an algorithm on another algorithm that behaves differently, because that won't make it work efficiently as you expect. Because each data structure has its own weaknesses and strength points. So an example for that, if there is an algorithm that tells you, give me the first element of something like the first elements that behave like this or that are superior than this, or you get my point. Then you're going to use ordered list because with that, once you finish and you want to get those first elements, you're just going to get a chunk of the first part of the list or the last part of the list, depending on what you want to get. Another example is, for example, there is an algorithm that tells you, give me a count of each element that exists in this list. Here, a hash map would be a perfect use, since you can use the key as the element that you want to count for, and you will have unique elements. And through those elements, you're just gonna keep incrementing and the value of that key, how many times you find that element. And you're gonna iterate through that. And if you want the count of one element, you're gonna search through the hash map in a logarithmic way, and this will be very efficient. The reason is that data structures are really important for performance. It's because of in computation there is a concept called locality, where you need to use the data that is loaded and the closest way to the CPU rather than getting from the random access memory where it's going to take much more time. That's just an example of my points, but another reason is because you need to iterate through the whole list for sometimes, and that will take a lot of time than just going to directly to the element that you want. That's another example. Now I'm going to talk about graphs. Graphs are basically just another type of data structures, and they're more like an abstract data structure, or should I say, uh, complicated data structure, but at the same time, it can be used so it can give us a very efficient algorithms and very good use cases, especially in geometric problems or in, for example, geographic problems that you can do in maps and stuff. And the graphs basically are just a combination of nodes and which they called vertices or vertex for one node that are connected with edges. And these vertices can have a value inside them or let's say a value inside them. Same as the edges, we can also assign a value to them, which is, you can call it a weight. And through that, you can use graphs to model a lot of things, especially the problems that have some elements that have a relationship with other elements in a way. Let's say, for example, if you store in cities and you want to calculate the distance between each city, then you're going to want to use that. A perfect example to use here, a graph where you can store cities in each vertex, and the edge is the road or the distance between that vertex and on another city. Another example is road networks. Sorry, node network is is what I explained. Uh, compute networks or social networks, and by social networks, you can use it like how Facebook is using it, where it's a vertex is a friend, and the vertices are how close each friend to friend. And from there, you have a very big social network where you can suggest new friends through your algorithm, where you can see the closest vertex to your own vertex, which is you. Sorry, I was going too much for the examples, but I just want to give a concrete way how we can use graphs here. And how can we work with graphs? Because since they're just an abstracted data structure, we need to implement it in our algorithms. And to do that, we need to find a way that we can do it in a efficient way, of course. And we can store data structure working. Sorry, we can store graphs either with matrix or adjacency lists. Both of these are good data structures that we can use to implement a graph. However, matrix is a little bit, let's say, have a bigger volume, and that will be not efficient to use in big scale inputs. Adjacency list, sorry, is a better choice for those cases. However, the matrix is much easier way to use and not complicated, since you can just link each vertex with another vertex by making the intersection of the column and the row as one, or you can have a weighted edge there and you can have a value there instead of a one. How can you traverse a graph? Because that's a really interesting, not interesting, but a fundamental thing here that you need to have through all the implementations of the graphs that you need to put. So we need, and here we have two of the algorithms that's been created, which is first breadth search and depth first search, which is basically a framework that we can use to implement our graph solutions that we need to do. And first breadth search basically is just a way that it traverses the graph through, let's say, by seeing all the surfaces of the vertex that exist, then go into the second level, then keep going like that. On the other hand, depth first search, it goes in a niche way where it's once it scans the first tree, it's gonna choose one vertex, for example, and it's gonna go deeply with it until it's finished, and it's gonna go to the second one. So each one has a better use case for the other one, depending on the behavior of the algorithm, as I said. So that's two ways that you can traverse your graph in an efficient way. Now we talked about graphs and their implementations. I'm going to talk about NP concepts. And basically, we have in algorithmic problems, we have P problems and NP problems. And what I mean by that, P problems are the problems that are resolved in a polynomial time. And that time is deterministic. And you can define it with a function. As I said, that complexity is defined. And we have that limit or constraint of that depends on the input, of course. However, NP problems are problems that are non-deterministic, and we cannot know when they're going to be resolved or how much time they're going to take to resolve. However, we can test the results to see if they're correct or not in a polynomial time. And through these two, we have another two that exists, which is NP hard, which is basically problems that are beyond NP. They're non-deterministic, but at the same time are hard. And what I mean by hard is we can reduce them to NP problems. That's the minimum we can do, but there still has to be reduced at the same time, and uh, we cannot know the results. We cannot test them in a polynomial time. And between the NP and P hard, there is NP complete problems, which they laid out and or like they intersect in both of the spectrums, which basically they're NP hard problems and at the same time are NP problems. What I mean by that is they are NP hard and they need to be reduced, but at the same time, the testing of their results can be resolved can be checked at polynomial time. And you may have the question now, since NP problems cannot be resolved at a deterministic time, then how are we resolving them at the first place? Sorry for my stuttering. And we can do that not just by a process, since it's not deterministic. We need to find a way that is a little bit probabilistic, let's say, or more in a human way, let's say, or in a chaotic way, should I say. And through that, we have combinatorial search, which is basically a way that that iterates through all the combinations that exist and tries to find the solution. While at the same time, whenever it goes to a bad road to find the solution, it can test that it's going the wrong way and it can backtrack and go to the original place and starts from again to find the best solution. This is a way that you can use, but it's very non-efficient in the normal polynomial solutions that we use in polynomial problems. And we can help this become a little bit faster through heuristics. And what I mean by heuristics is finding a method or strategies that are dependent on that same problem to help it find a way to get to the solution faster. And these heuristics and strategies are more like a human way or like a human way of testing, just to get a little bit easier to find the solution. But at the same time, we still have to try multiple combinations to find, let's say, an approximate solution, because NP problems, we don't guarantee to find the most optimal solution. We guarantee only like the third best solution or three times the best solution. And these strategies can be, as I said, can be dependent on the problem. For example, in Sudoku, you can put a heuristic or a strategy that says start always with filling the least free spot, and that helps to even when we're solving Sudoku, we choose the spot that is full, and we have only one spot is empty. That helps us find the solution much faster and just be one less step from the solution. Aside from heuristics and strategies, dynamic programming is also a big help to resolving NP problems. And dynamic programming is basically recursive algorithms or combinatorial algorithms plus cache. And what I mean by that is, while trying to find the solution through our combinatorial search and go into the wrong way, and you want to backtrack, you don't need to backtrack all the way down. You can backtrack just one point where the solution is still good, and you can go from there. Another example is when you're recursing to an incremental problem or recursive problem, and your recursive function is going through a multiple tree where it's instantiate each recursive function. And through that instantiation, there is some, let's say, trees that overlap, and they have like the same route repeated in the same time. What I mean by that, there is some recursive instances that are the same and calculated multiple times. And with dynamic programming, we can like store that value that's repeated And we no longer need to calculate each time we need it in that recursive tree. We just need to get it from the memory. And that's where it's stored in the cache. That's what I mean by recursive algorithms plus cache. And this enables us with more performance from from our either recursive or resolving the NP problems that we're doing with combinatorial search. A drawback from this is if you use uh, the cache to store all the recursive instances that you have there, then it's gonna be a little bit overwhelming for memory, and it's gonna get a lot of space that's it's gonna be counterproductive. So a way to resolve this is to only store the last two recursive instances. Most of the time, that's what you're using, just the last two steps, for example, in Fibonacci problem. And yeah, that's pretty much it for dynamic programming and NP problems. Now I'm going to talk about reduction. And what do we mean by reduction as a concept is trying to transform a problem A to a problem B, where the prob the problem's solution, let's say, or purpose is not the same thing, but the behavior and the hardness of that problem is the same thing. And that will help us not by finding the solution itself, but by finding the hardness of the solution and how efficient the solution can be resolved. For example, if we have an A instance that's been reduced to a B instance, and we know that the B instance is an NP problem or an NP hard problem, then we're sure that the A instance is at least NP hard problem. And if we found that the B instance can be resolved at polynomial time, then we're going to be sure that the A instance can be resolved at polynomial time. That's how helpful it is. And you might think, why do we need this reduction just to know the hardness of the problem? But this is really helpful for an algorithm design perspective, because when you have a problem at hand and you cannot find a polynomial or an efficient solution for it, sometimes you waste in time because that problem is already NP hard and you don't know that. The best way to save your time is to use reduction, where you can just try to reduce it to an NP problem or a problem that you think that's isn't the same hardness for it. Once you reduce it, then you're sure if it is an NP hard or an NP problem or an NP complete problem, just based on the reduction that you made. And you're no longer wasting time trying to find a polynomial time solution for an NP hard problem. So sorry, that's what I explained. I forgot to move the slide, but that's what I said. And a basis of a problem that you can use to make sure that your problem is NP hard or NP complete is you can basically just there's multiple NP hard problems, but you can only use this four, and this four are enough to reduce any problem that exists in real life, which is tree SAT, which is a tree satisfiability problem, then the vertex cover, then the click problem, then the Hamiltonian cycle problem. So now we have, and we understand a little bit of, or we have a general idea of algorithm design, let's say keys or variables. Now we can conclude that the approach in algorithm design, aside from understanding the problem and knowing the input of the output, because those are the first uh, and the fundamental things that you need to define before resolving your problem. After that, what matters is just building your algorithm as a puzzle block or let's say choose containers that you need to link together to make your problem to resolve your problem. And those containers can be choose using the data structure choice, the accuracy, what I mean by that, the correctness, and the hardness of your problem, and the performance, which is data structures most of the time. And what I mean by hardness is what I talked about in the NP concept and reduction, since If you reduce a problem and you find it's NP hard, you don't need to think about polynomial time. You just need to go for either a combinatorial search or dynamic programming or the NP problem solutions that we have. So from here, we can conclude that now with our algorithm problems that we have now in real life, they're no longer about making a new innovation, for example, creating the new Dijkstra algorithm. Because just like all the math was laid out for the physics to work, same goes for algorithms. All the tools have been laid out and the research and has been created through multiple iterations. And we are on the limit for that. If there is an innovation, it's going to be like through 10 years to 10 years. It's not going to be through your problem because all the problems have been abstracted and been resolved in an abstracted way. You just need to abstract your problem and find the equivalent abstraction of it that's been resolved and use that to find your solution. And that's the fruitful parts that you could understand from here to use for building your new algorithms. You no longer need to think about how to build it, but what is the problem really? Like I said, what known tools should I apply? And what should I search for or try first so I can test if it works? That's the main questions that you should ask. And as a conclusion, I could say like developing the sense of a pattern recognition is what matters because at the end of the day, what helps is understanding the problem and trying to abstract it to get to link it with the abstracted solution that already exists. And through there, you just need to link the puzzle pieces and make let's say the fierce initial solution that you can iterate from it. And yeah, that's been my explanation or my presentation for algorithm design manual. I hope you understand it. And yeah, thank you for watching.